Hello, everybody. So, today we will learn a very interesting algorithm, and this is called the wave collapse algorithm. And using this, we can create very interesting and quite logical 2D maps. So, here in this map, as you can see, similar kinds of tiles are actually sticking together. So, we have a yellowish beach tile and a bluish water tile, and we don't have a lot of mountains within beaches and waters because that is quite illogical. We may have some forests here and there, but wherever we have mountains and forests or grasslands, you can say, they are sticking together. So using this algorithm, we can create this very interesting phenomena. So we will see how we can do this today. So let me first show you the tiles that we want to use for this video. So these are our four tiles. Very simple, and I will also link in the description. I also have another one. The mountains look slightly different, but I like this one more, so we will use this. Now, this has already been imported in my Godot project and the terrain too, this one. So what I have to do is I have a new scene. I will create a new 2D scene, and here I will add a tile map layer. And here in the tile set, I have to click on new tile set. And here we will import our tile set. As we can see, we have our tiles, and these are our four tiles. We'll also create a canvas layer for our button that we will click to randomly generate our map. So we'll write randomize. Now one thing is remaining in our node 2D. Let me also rename it to wave collapse map because this is the algorithm we are using. And let me save it in the scenes. And the last thing is we have to attach a script. So wave collapse map.gd. We'll save it in the scripts folder and we have our script. Now in our script, we will start by defining our tiles. So we have a water, and this will be a vector 2i 3, 0. Where are we getting this? If I go to tile map layer and tile set, we can hover over the water and we have atlas coordinates as 3, 0. That is what we are writing here, which means from the tile set, this has the coordinate 3, 0. Then comes our sand, and we already know this is a 2, 0. Then comes our grass. You can also name it forest. I'll name it grass. This will be a 1, 0. And lastly, we have our mountains. Let me just name it hill. This will be vector 2y of 0, 0. Now, after defining our tiles, let me create a variable. We'll use a var keyword this time as tile types. This will be required later. And we have four kinds of tiles. So we'll just add these four tiles that we have created now. So grass and hill. Then we also have to define some map width and map height. So this is basically how many tiles we want in the map. So let me give the map width as 25, and let me also expand this because this may not be required anymore. Then let me give the map height. So var map height as 25 again. Then we have to have some cells. This will be an empty array for now, and collapsed cells. We'll explain this later when we are using it. And this should be an underscore, not a plus. Typos. Now, after defining these things, we have to define some rules that we have to follow while creating our map. And this is the fun of the wave collapse algo. So this rules is called adjacency rules. In other words, what this means is what tiles can be adjacent to every tile. That is what these rules define. So we'll create it as an object, and here we have to define the rules for every tile. So adjacent to the water tile, what other tiles that we want? Another tile can be another water tile and a sand tile. We may not want a grass tile directly side by side a water tile. A tile can be next to a sand tile. So next rules will be for our sand tile. So next to a sand tile, we can have a water tile, another sand tile. If it is a thick beach, uh, not only thick, it can be next to the next water tile also. I mean, you get my point. It can be a long, thin beach also. Then also every sand should have another sand next to it. Sand, of course. And also it can also have a grass next to it. So we have our plain land starting. Next comes our grass tile. So grass can have a sand next to it, another grass next to it, also a hill next to it. And lastly, we have our hill. So next to a hill, we can have another grass or another hill. So that is what we want. We can also remove the hill. What that will do is it will basically create one hills. So grass will generate one hill, and next to the hill another grass will be generated. So we will get one hills. But yeah, this will make it more fun. So these are our adjacency rules. And lastly, we have to define one more variable. And this is a node that we will take from our scene. So on ready where tile map, we will take our tile map layer because this is where we have to place our cells. Now inside my function ready, so whenever we are basically starting our game or our map, whatever, we have to first initialize a cell. So init cells, we have to call this function, and then we have to basically call the wave collapse function. So wave collapse, and lastly, we have to apply tiles. That's all. So wave collapse will basically set, like in our grid, which position should have which tiles, but that doesn't necessarily draw the tiles. So to draw the tiles, we'll have to call another function that I'm naming here as apply tiles. Now let me write these functions quickly so that we are not getting errors. So init cells, this is our one function. Let me do it fast. Then another function is wave collapse. There can be another pass here. And lastly, there will be a function called apply tiles. Let me also give a pass. Now, when I save, the errors are gone. Now, what do we need to do here? So first things first, inside our init tiles, we have to first set all of our tiles. So here we have the empty cells. This is already defined here. We are using the same cells, and also we will take the collapse cells. Both are empty for now. Now for y in range of map height, we want to look through the map, and in our cells, we want to append another empty array. So our cells is an empty array. Now for every y, we are appending another empty array. So this is kind of becoming like a 2D array. Now for x in range of map width, what we want to do is for the cells y, so the cells y is basically, so we have a y in range, and inside the x is looping, and then slowly the y from the outer loop is also looping. So whenever we have a y, we will take that array, so basically that index of the 2D array, and we want to append our tile types. So we will basically append our tile types. Basically this one, water, sand, grass, and hill. But we will not directly append this one. We will create a duplicate of this and append this. So what this means is we will get a 2D array where every cell will have 4 types. So if I just, so after the init cells, let me do a print of cells, and we'll have an idea what we are getting. So let me run the scene. And in the output section, you will see that I have many things. So for example, we are getting a lot of things. So 30201000, 30201000, and this is there for everything. Why? Because these are basically the values of this. So vector 2i is basically the vector, the real values are this, and that is what we are getting. Quite expected. So now our init cells are done. Let's now take a look at our apply tiles function. The wave collapse function is the most important, but the apply tiles function is more simple and we can take care of it soon. So this is how we can draw our tiles. So once again, we have to look through the map. So y in range of map height, and for x in range of map width. So we can assume that after our wave collapse function, we have a very good idea that which tile should be placed where. So we will create a tile like this, and we will take the cells yx, and whichever is the value remaining, we can pick it up with 0, basically the first value of the current index of the cell. And what we will do is tile map dot set cell, and here we have three arguments. The first one is the coordinates. So this will be the vector 2i of our x and y, basically the coordinate in the map. Second is the source ID of the tile set. Since we have 1, this will be 0. And then we will place our tile. So right now we have nothing. We may have something. Let's see what we get. So we are getting only water, since the first value is a water. If we change this order, this will change. The idea is how to create a very interesting map. And to do that, let's start writing our wave collapse algo. So the idea of the wave collapse is that, so right now every cell has four options: water, sand, grass, and hill. So if I run, we have only water. There is an issue now. So what we want to do is, since we have one tile as water, the next tile should be limited to either water or sand. So all water is a valid possibility, but since some of the tiles will be sand, the next possibility will again change. Some could be grass, and we no longer can have water next to it. We should have sand, grass, and hill. So that is how we are basically collapsing the possibility of what tiles we can use for every cell. So for one cell, we have a tile. The possibility collapses for its adjacent cells, and so on and so on. And that is how a map is generated. So that is basically the idea of the wave collapse algorithm. Very interesting concept, and also very easy to code. So first of all, we will do a randomize, and then let's start from a random variable, like some random index x and y. So we'll take a random integer, and we'll take the modulus by the map of width, and same goes for the y value also. So start y equals to rand I modulus of map I. We will then have to call a function called collapse cell, and here we will pass a start x and start y value as vectors. And this function will basically do the job of limiting the options of tiles that can be used for a cell. Now this is calling only once. What we have to do is call it for every cell. So we'll create a while loop here, and we'll take a cell. Now how can we take a cell? We will take a cell by their lowest entropy. So find lowest entropy. So in physics, you may have studied, we call that entropy is the measure of disorderliness. So whenever a cell has multiple options, we can call it disorderly because we are not sure what option to take. But whenever a cell has only one option, let's say, we are certain what we need to do. So there, the entropy is low. So that is what we are checking. So if cell equals to null, in that case we'll break out of the loop, and otherwise we will repeatedly call the collapse cell collapse cell with our cell. So whatever value of the cell we get, we will call that. Now there are two undefined functions, and that's why we are getting some errors. So we'll create a function called collapse cell. It will have a position, let's say, and we will also have another function. This is called find lowest entropy. And this is basically looping through the map and finding whichever cell works for us, like something that has low entropy, and that is what we need to pass. So let's now write our collapse cell function. We will start by extracting the x and y values from our position. So where x will be post.x and where y will be post.y, because that is what we are passing here. So basically x and y are our start x and start y values. Now, whichever is a cell, we will pick a random index of that cell. So we'll do rand I percentage of cells yx dot size. Now this value is 4 because initially every cell has 4 options. It is either a water, sand, grass or a hill tile. So what this means is randi creates a random integer and we are moduling it by 4. So we are getting a value of 0, 1, 2 and 3. Basically we are picking one tile and so we'll write chosen tile equals to cells yx and we'll take the random index, basically shortening the 4 tiles to one tile, and in the cells yx we want to assign the chosen tile. In other words, we can say that we have collapsed one cell already. So for one cell, the 4 options have been reduced to 1. And we also have a function called collapsed cells, which is empty initially. But since one cell has already collapsed, we can pass it over there. Now, whenever we have collapsed one cell, what happens is the options for its neighboring cells are also limited. So, for example, if one of the cell becomes a hill, suddenly her neighbors can no longer become water. So the options for the neighbors of the collapsed cell is also limited. And hence, we have to write another function called propagate constraints. And we will pass the position here. And lastly, we will return true. Now, because we are restricting the options for the neighboring cells also, and this is the reason why we can have the interesting phenomena of similar tiles sticking together. If we just picked everything randomly, this will never happen. So now we have to write another function called propagate constraints. Now I hope you're getting an idea is that if we are calling these functions again and again inside a wave collapse, what is supposed to happen? Now for all the neighbors, we will again call the wave collapse, like the collapse cell. Those cells will be picked up. Now the size will no longer be 4, it may be 3 or 2. And as a result, for the whole map, um, we will get very logical options for different cells. Now, uh, how can we propagate the constraints? Again, we will first extract the x and y positions. Now, we have to take the relative indices of our neighbors. So, we have some neighbors and we can take their indices by vector y. And here I will write x comma y minus 1. Now, if you think carefully, this is actually our up. Now, next, let me write x plus 1 comma y. This is our right. Then comes our x comma y plus 1. This is our down. And lastly, we have x minus 1 comma y. And this is our left. So these are 4 directions. Now you can take the corners also. But we won't like to take that here. But this will also be very much valid. Why we don't want to take it is because if we take 8 corners and we propagate the constraints there, what will happen is the map will have more of similar kind of tiles. For example, if we start with a sand, we may have very less hills because all the 8 corners will be either a water or a sand or a grass. Now for water and sand, we will not have a hill. For grass, we may have a hill, but that again in one of 3 conditions. So that is a possibility wherever if we take only the up, down, left and right, we may have more variety. Now there are other ways to tackle this, but to keep things simple and sweet for this video, we will take only 4 directions, but we will also write it and this will also work. So let me take plus 1 minus 1. So this will be upright and then plus 1 plus 1. This will be downright. Then minus 1 minus 1. This will be left, and since this is minus 1, this is basically up left. And lastly, we will have a down lift. So this will be -1 and a +1. But we will keep these four values as comments for now. Now, after we have our directions, we have to loop through our directions. So for neighbor, in neighbors, what we want to do is we first want to check that the real value, like the real index of our neighbor is not out of bounds. So the x value should not be less than 0. I mean, if this is less than 0 and other things, we will just continue and we won't do anything. That is what we want to do. So the x should not be less than 0 and the neighbor dot y should also not be less than 0 and the neighbor dot x should not be greater than equal to the map width and the neighbor dot y should not be greater than equal to map dot height, not dot map underscore height, because that is the variable we have declared above. Now this may happen. Why? Because we are taking a lot of -1 and +1 values. So it is possible that for some of the neighbors, the value will be out of bounds. So we want to exclude those situations. Now once we have everything, we want to update the neighbor constraints. We will pass the position, which is the current value, and the neighbor. Now another function. But trust me, this is the last one. So let me write the func update neighbor constraints, right? No spelling mistake. I hope not. So here we will have two things. One is a cell position. Another one is a neighbor position. Now here, let me create another empty array called possible tiles. Now here, for cell tile in cells, we will take the cell position dot y. Cell position is basically we are taking the current cell position dot y and then the cell position dot x. So this may have multiple values, 2 or 3 or 4 could be 1 also, and we are taking 1. Now what are the allowed neighbors? We will create a variable for allowed neighbors and we have to take it by the adjacency rules and we will pass the cell tile. In other words, if the cell tile is a hill, from the adjacency rules, we will set this value, grass and a hill. So this is our allowed neighbors. Now for tile in cells, neighbor position dot y, comma neighbor position dot x. Now here, what we want to do is we want to check if the tile is in the allowed neighbors or not. So if tile in allowed neighbors and not tile in possible tiles. So tiles should not be present in the possible tiles. This is empty initially, and the tile should be present in the allowed neighbors. Now, in that case, what we want to do for our possible tiles, we want to append our tile. Now, lastly, all of these things doesn't make any sense because these are all internal variables. What we have to do is we have to set the value in our cells. So in our cells, neighbor position dot y and the neighbor position dot x, what we want to do is we want to set the possible tiles. So the possible tiles for that particular neighbor has been updated. And as we are calling the collapse cell repeatedly, and this whole process is happening repeatedly, um, in every iteration, we will have an update over here. And a time will come when all the cells will have only one definite value. And we can create a map like this. Now, why is there an error? Must be some issue with the function name, looks like. I think this is constraints. It is constraints. Now it should be gone. Update neighbor. Okay. This is constraints, typos. Still, there is some issue. And this is actually an indentation issue. It should be within the for loop. Now it will be resolved. Now, if we run the function once again, let's see what we get. We have a very interesting behavior. We have one grass and four sands. Now, why is it not doing anything else? Is because in our collapse cell, what we are doing is we are basically mm, in our wave collapse. If we see, we are only doing it for one of the cells. What we have to do is we have to do it for the whole map, and that is something we are not yet doing. And once we do that for the whole map, we will have this very interesting phenomena. But before that, let me do one more thing. We have a button here, and let me add a signal to the button. So it will be a press signal. And here what we want to do is we want to generate our map. We don't want to print cells. I think we can remove it. It's no longer required since we already have an idea what is happening. And here in the signal, I just want to do this. Now let me run once again. And now if I click on randomize, you will see that in one portion of the map, and we are also getting some sort of an error. It is in line number 45. Okay, in line number 45, I think they are having some issues with the neighbor index. So it is trying to access the index 25, and so the neighbor value becomes 26. And as a result, what happens is, as a result, um, they are getting an error. But ideally, this should be handled in it should be handled here. If these values are less than 0 and this is greater than map width and map height, this should continue. And this update neighbor constant should not be called. But yeah, anyway, I think there is some sort of an issue, some edge case is there, but we will see that. Let's first write our update entropy and let's see how we can do this for the whole map. Now, in our find lowest entropy function, we will first assign the minimum entropy value to 9. You may also consider this as a cell has 9 possibilities of what the tile could be. Now we know that there are only 4 possibilities, but we want to set the minimum entropy value to a very high value, and so we are assigning 9. Anyway, this will be changed. Now I will set a candidates array as an empty array, and I have to look through the map once again. So y in range, map height, and x in range, map width. Now, we want to check if the current xy is part of the collapse cells or not. If it is, that means we have already decided what is the tile for that cell, and hence the entropy should be 1. So we have to first check and um, the possibility. So vector x comma y in collapsed cells. If it is there, then we will simply continue. In other words, we won't check any entropy or anything. Now, let's get the real entropy. So the real entropy is, let me write another small function for get entropy, and we will have to pass x and y. No worries, we are writing another function, but this is a really small function. So func get entropy, and we have the values of x and y. We will first check that both x and y are inbound, so x should be less than 0. Well, actually, they should be greater than 0. Y is less than 0 and x is greater than equal to map width and y is greater than equal to map height. Now, we know for a fact that this is outside the map. So in that case, we will return 9. In other words, the entropy value becomes 9 because we don't want to set any cell outside the map. Otherwise, if they are within bounds, then our entropy value is basically whatever is the possibility of tiles in that cell. So we basically have to measure the cell size. It will not it will be 4 for many, but it may not be 4 also because we are also changing these values inside our collapse cell and all the functions that we have written. So what we will write is cells yx dot size. So this is our actual entropy value that will be assigned here. Now we will check if the entropy value is less than equal to 1. In other words, we already know what is a cell. So this should ideally be in the collapse cells. But anyway, in any case, if this is 1 or less than 1, then we will simply continue. Now, if entropy value is less than minimum entropy, now this will always be the case. In that case, what we will do is minimum entropy value should be assigned as the entropy value. And wherever we have the candidates, there I want to set the vector 2i of x comma y. Now, at last, we will check if the candidates dot size, if this is greater than 0, in that case, what we want to return is basically one random index from the candidates. So candidates, and here we will do rand I percentage of candidates dot size, and if none of this happens, we will return null. So this is basically if there are some out of bound situations, we will return null. So now we have everything set up. So now let's take a look at the flow of what happens when we click on the randomize button or when we are starting our function. So initially we have init cells. So we are basically assigning tile types to all of our cells in the 25 cross 25 array because that is our map width and map height. So once the init cells is done, um, we will do the wave collapse. And lastly, we are doing an apply tiles. Basically, whatever tiles we are getting, we are applying. Now, in the wave collapse, we are basically setting our tiles. So, how are we setting? We are taking a start x and a start y value, and we are starting to collapse cells, the neighboring cells from the start x and start y. So, inside the collapse cell, what we are basically doing is we are picking one random index, and basically we are setting with a chosen tile using the random index, and we are then starting to collapse cells starting with their neighbors. So the neighbors first, then the neighbors will be set, and then their neighbors, and when their neighbors are set, then their neighbors, and this is how we are propagating the constraints, and we are updating the neighbor constants, and so this is what we are doing only once, but this needs to be done for all the cells. So as long as basically we are in the while true condition, and we are basically finding the lowest entropy for all the cells and collapsing the cells. Now, if the cell becomes null, then we are breaking. So when will it become null? So in the get entropy function, in the end, we are returning null when none of these things are working. So, and this will only work when we have basically covered all the cells, and yeah, the only things that are remaining are out of bounds. So in that case, we will return null and we will break out of this loop. And yeah, so now if we run, it should work. So let's see. And we are having an issue, and in this is in index 25, and I think this is in line number 68. We are having some sort of an issue. Now there are a couple of issues that we came across, and the first one is in the gate entropy, we are checking the out of bounds with and conditions, but this should actually be an or condition. If we were checking if the value is within the map, then we should be using an and condition. So for example, greater than 0, and less than width and less than height, then that should be an and condition. But here, since we are checking if this is outside, if any of the cases is true, this is outside. So here there should be an or. And in another place, in our propagate constraints also, uh, this is wrong, because we are checking if any of the neighbor is basically outside the map. And so again, it should be or and not an and. Now, let me run once again. And we still have some issue, and that is we are trying to access the index 0 in case, I mean, whatever is the case. So there is another issue here, and we need to make sure that we are not accessing 0. That's all. Now, how I will do that is very, very simple, and that is Before setting our cells, we will check if the cell yx dot size is greater than 0 or not. Only when this is greater than 0, I want to set the tile and set our tile map. Now, our code should work perfectly fine. So let's run once again. And as we can see, we have a map, and clicking on the randomize, this is also changing. Now, this looks very small. So what we can do is, in our project settings, below our display, we can make the scale as 2. And now let me run once again. And we have a beautiful map created out of wave collapse. So this is like a lot of mountains and forests. And within the forest and mountains, there is some sort of a small lake. Now, we haven't used the corners. So in the corners from the water, we can have some grasses and mountains. Now, this is a very simple application of wave collapse algorithm. Now, there are a lot of more ways to use this one. So for example, um, here in this map, this is a very top-down map. We don't have corners and any other things. So we are only changing the entropy values of the neighboring cells. But there will be cases when we have to change the like the neighbor values of the next neighbor also. So the immediate neighbor we have to change, and the neighbor after the immediate neighbor also we may have to change. And using those conditions, we can actually create more detailed and more beautiful looking maps. Now going forward, we will make many such maps. So that's it for this video, folks. And if you have learned something new in this video, make sure to like, share, and subscribe so that I can grow the channel fast. And if you want to talk with me regarding game dev or any other technology stuff, I have my Discord server. I will put it in the description below. And make sure to join there. And I will see you soon with another very interesting video. So see ya.